Okay, so welcome to CS484, Computer Graphics Fundamentals. So today we're going to talk about texture mapping. So let's just quickly review what we talked about on last class, which is about two-dimensional and three-dimensional representations, and then we'll get into some terminology and then start digging into the details of texture mapping. Okay, so one of the things we talked about last time was 2D graphics. So we were talking how would you represent elements in this context. So we talked about tile mapping as a way of drawing backgrounds with data, with cells, so we can kind of create a low memory footprint. We talked about sprites, being able to put any kind of image anywhere on the screen. And we talked about polygons as a way of representing shape information. All right, and then we increased that, from going from 2 dimensions to 3 dimensions. We talked about a polygonal representation. So we have objects that we would like to represent using polygons, and so we typically need to take a object and break it into different kinds of surfaces. Surfaces might have different kinds of material properties, such as different texture maps, color, those kinds of things. So once we have our object broken into these different kinds of surfaces that have common properties associated with them, then we want to create polygons out of those surfaces. All right, so we were using the example of a cylinder. So you might take the top and bottom of the cylinder and then the actual cylindrical surface itself and create a polygonal representation. And pretty much the general rule in 3D is that anything can be represented with a triangle, because the triangle doesn't bend. It's the simplest thing you can pretty much produce, and they're easy to render. So we have polygons, which are triangles, and polygons essentially consist of edges. So you have a sequence of edges and vertices that those edges connect to. And there is some significant benefit to sharing as much information as possible, because then if you wanted to draw a silhouette outline or so on, you can make use of that information to figure out where the creases are or where's the outline. If you kept everything separate, then even two neighboring triangles would look like completely two separate things to the computer, because you have different positions. Even if the positions are exactly the same, there's really no way for you to connect the dots for the computer unless you say you're using index data. In other words, this polygon uses vertices 1, 2, and 3, and this polygon's using vertices 2, 3, and 4. With that, you could at least reconstruct it. But if you have one polygon that's using vertices 1, 2, 3, and another polygon using vertices 4, 5, 6, then there's no logical connection there. So you need to keep that in mind when you're creating a polygon representation. Okay. We talked about how various graphics cards will handle this. We use OpenGL specifically because we have vertex arrays, which basically describe, how is the data laid out per vertex, color, normal, position, and so on. And then we have the mode that we should draw a list of vertices, and that could be points, or it could be triangles, a line loop, triangle strip, and so on. All right, and then we discussed, well, how do you create these kinds of representations, and typically use some 3D modeling software. You'll have a team of artists typically will work on the 3D element of it, and then you will work on actually taking the input data and getting it ready to render with using draw commands. Okay, and then we talked about a variety of applications. We talked about sprites and tile graphics, like the Super Nintendo or the original Nintendo or the Atari, some simple representations there. And then we talked about 3D scenes and scene graphs. So, what are some common ways of using these 3D representations to be able to move around in a 3D world? In some cases, you can get away with just using a two-dimensional SAL grid to represent your world data and then reconstruct a 3D model out of that. Or you can just start off with a complex scene graph, with lots of models. And we discussed how pretty much every major 3D engine out there is a scene graph of some kind or uses that methodology. The key word there was a directed acyclic graph. That was the one key word to remember about a scene graph. And then lastly, we talked about collision detection and response. So collision detection, we used a very simple case of a axis aligned box. So you're looking for overlaps with the, say, the left and right planes. Or minimum X and maximum X planes, minimum Y, maximum Y planes. And you can detect those overlaps. And if you overlap in every single dimension that you're interested in, then you have a collision. So after you've detected a collision, then you have to decide how will you respond to the collision. So we talked about enemies and frenemies, right? Maybe it's in a game context, it might have to do with, did an enemy touch you, right? Or did you fire a fireball and then it bounces back and hits you? What do you do in those cases? Those are often design choices. In the simulation environment, you may need collision detection or response to make sure that if you're simulating a construction vehicle and maybe it's got a crane lift or something on it, well, you cannot have, since it's physically impossible for it to self-intersect, right? Then you should make sure that you detect if it intersects with itself and what the response ought to be. Okay, so you may need to use some advanced physical calculations. It really depends on your audience, right? So if you're looking like vintage two-dimensional games, you know, it might be simple just to do an axis aligned box and nobody's going to care. But for advanced simulation, you might need to simulate, you know, an advanced piece of geometry. Okay, so we looked at different applications for 2D and 3D representations, and one of the reasons why we focus on those particular applications is because Ludum Dare is starting on Friday. All right, so if you've not yet created an account, I was going to go over to the Ludum Dare website because the voting is on for the theme. Okay, so you can see my votes. I'm not. I voted against the ones I didn't feel like doing, or I thought they're too simple. I don't know. I have to think about it. But basically, so round one, I was voting in round one. So they had different things like take care of the egg or leave something behind. And so they have different rounds of voting. And since we're done with those, now we're in the final round. Okay. Oh, I guess I'm logged out, but that's all good. So anyways, Friday afternoon, let me move this out of the way. Friday afternoon, 1 hour, 1 day, 22 hours and 19 minutes away. So we're less than 2 days away. And that means at 2 o'clock in the afternoon on Friday is when you can let all the pandemonium start, you know, just go crazy, have fun. I'm going to participate this year. So let's see what I can come up with. I don't use 48 hours. I give myself 8 to 12 hours, and that lets me have a normal life. Otherwise, it can be pretty intense. You need like a full day going into it and a full day afterwards if you're going to do something like that. But I think that you can do something pretty awesome in 8 to 12 hours. You could at least get a game finished, and I think that's pretty good. So that is Friday. So that is the homework for Friday. Whether you choose to submit it or not is a personal decision. So I will not make you submit it, but I think that it would be a good idea to do that. Okay. Okay, so let's get back to the slides. So the terminology, all right. So we're going to start to hear a lot of things in the coming weeks. And these are things that we need to kind of incorporate into our vocabulary so we understand what's going on. So a frame buffer. A frame buffer is typically the pixels that are going to be drawn directly to the screen. Okay, that stores our image that is going to be presented to the screen. Typically, we have two frame buffers. We have a front buffer and we have a back buffer. The front buffer is the currently displayed image on the monitor, and the back buffer is the current image that we are writing to. And it is important to have double buffering. We call that scheme double buffering. But there are other ones like triple buffering that you keep 2 images on the back instead of just 2. But the benefit to double buffering is that if you're, the problem with, I guess, single buffering is that as the screen is, your monitor is refreshing the image, you might still be drawing to it. And so if you haven't finished drawing a complete frame, you might get half of one frame and half of the other. And if you're clearing the screen in between frames, then you could potentially be getting, you know, data that's not quite updated. So what we do is we render to the back buffer so that when we present the frame, it's a complete image and it doesn't have any, it's not different every time. So single buffered applications have a tendency, especially if you're running at a frame rate that's not ideal, to be flickering, and you'll see tearing from one image to the other, and it doesn't look good. All right, so double buffering is pretty much standard, and in order to do that, we have a frame buffer. The second thing that you might see is a render buffer. And this is used if you're going to render to an off-screen image. And render buffers are used for if you want to render basically a screen worth of information, but you don't want to put it in a texture map. So it's a way of getting a rectangular region of the screen that you would like to render to and use for later without using a texture object. All right. Now, a texture is, we can just be generic and just say that it represents an array of pixels. All right. And it could be a one-dimensional array of pixels, a two-dimensional array of pixels, array of pixels. But the idea here is, you know, if you were to ask most people what they think of when they mean texture, what do you think that they would respond with? We get some solicitations from class. I ask you, what does texture mean? You ask your mom, what does texture mean? The texture of an object? Okay. Let's try not to define it with the word inside of it. Like somebody says, what is a texture? That's hard to do because it's a texture, right? So we just kind of think about it. But how would you describe texture to somebody who maybe never heard the word before and we're not talking graphics? Texture. How something feels? Okay, so yeah, if you were to touch it, it's what it feels like. Okay, is it flat? Is it smooth? Is it bumpy? Is it rough? Okay, how does it feel? What else? I could go for that. Image on an object, you know, like somebody gets a t-shirt, you know, and they have an image printed on their t-shirt, you know, this is kind of the same idea, you know. Okay. So yeah, another way to think about it is a texture represents, I guess, what it looks like. You know, if you were to approximate, like, kind of how does it deviate from a flat surface, right? So if you have a flat surface represents normal, a texture describes how it differs from a flat surface. Okay, so for instance, it could also represent the detail of a surface. All right, detail. So for instance, if you're talking, you go to the playground and you have a flat concrete surface. Well, the surface doesn't look, I mean, it might look flat, but it doesn't look like a solid color. So it might have a pattern associated with it. Okay, so texture. So we use the word texture kind of as a way of saying that we're going to apply extra detail to a 3D model that wouldn't be there normally, or to represent surface detail that we don't have yet. But in a general sense, we can also think of the mean as just some input of image data.
We call a texture just like a physical description of an object?
A physical description of the surface of an object, of the surface. So we're using like a polygon representation or surface representation to describe the actual 3D shape of the object. But a texture map because it's an image, right? If you were to, like this room, if we were gonna create a model of this room, the floor would be flat, but we would use a texture map representing the carpet. So we'd take a picture of the carpet and then we would apply that as a texture map on the floor. And then when we look at it in a 3D preview, then we're like, okay, yeah, I can see that there's carpet on the floor. It's kind of an interpretation, but instead of 3D modeling all the fibers on the carpet, we're just kind of creating an approximation to that. All right. Okay. A color buffer. All right. So a color buffer is, I think it's fairly easy to understand. You just have to recognize when you should call it a color buffer. Okay. So color buffer is basically an image that stores color information. Okay. So a PNG or a JPEG of a photograph you took as a color buffer, essentially. Okay. And we use that to contrast with a depth buffer. And a depth buffer is going to store Z values, which we're still talking about that. So we're not quite to depth buffering yet. And we have a stencil buffer, which is another way of marking perhaps where we've drawn in the current image, or so we have different kinds of buffers that are used to store different kinds of objects. So in reality, color buffers are typically, we might think of it as what type do we put in there, all right? It could be an integer, it could be a floating point number. The depth buffer, we're typically storing a single value, which is the current Z value, and the stencil buffer is typically a very small integer, like an 8-bit integer, for instance. Okay. Some more terminology is a packed pixel. A packed pixel is basically when we have several pieces of color data and we put them together. So a 24-bit color or 32-bit color, where we put the red in the bits 16 through 23, or actually 16 through 23. Green, we put that in bits 8 through 15, and we put blue in bits 0 through 7. That is a packed pixel. In other words, we're sticking all of the color data into one simple type. So OpenGL has some ways, well, most graphics need to have a way of unpacking those pixels. So the pixels are a convenient way of shrinking the data, but in order to use it in a realistic way, we have to have some way of unpacking those pixels. Okay, so let's talk about image data. So image data is an ordered two-dimensional array of color information. That was one way I was thinking about how to describe it. Okay, an ordered two-dimensional array of color information. And a lot of times what we'll do is we'll say, let's put the first, say, row of information as the first subarray, okay? The second row is in its own array. And so we basically have like an array of arrays here. And then each one of these elements stores the actual color information. So generally speaking, we lay out, pixel X, Y at 0, 0 first, and then we put pixel X equal 1, Y equals 0 next, and we pixel X equal 2, Y equals 0 third, and so on until we have basically gone row by row, line by line, or I guess column by column, row by row. So here's an example of how you might think about this if it was in C++. So maybe we have a type that represents a color, and the image basically could just be have width times height data, right? That's the number of pixels that you need to store that information. And we could write a method maybe called getPixel that takes in the X, Y coordinates. And in order for us to map this to a one-dimensional array, we could say, let's take the Y coordinate and multiply it by the width. So if the width was 256 pixels, then we basically make sure that our Y steps us on in the array to the appropriate starting position. And then we add the X coordinate, which offsets that. So we're actually looking into it. So, so this is the way to return or to address a pixel in a one-dimensional array. All right. And if we want to put a pixel, then we use the same calculation and we just assign the color to that element in the array. So this is important to remember, Y times width plus X, because this is generally how you do the address of a image pixel. So as I mentioned, you have to take into consideration what kind of type are you using. So for instance, if I wanted a 24-bit color and I have red, green, and blue, I might use an unsigned char to represent each red, green, and blue, right? And there's 3 bytes there. This, of course, if you were just writing a binary file, would just be laid out, red, green, blue, 1 byte at a time. Maybe I want to store a high resolution image, so using a floating point color representation. So I might actually use a float for RGB and A. So if we have an alpha channel, so generally speaking, you just lay out each channel right next to each other and then go pixel by pixel. So this one might take 16 bytes per pixel. This is pretty expensive if you think about it, although it's not uncommon to actually write out to a image inside your GPU that is, say, 12 or 16 bytes wide, okay? Because you may want to move that or have that, maintain that accuracy, okay? Lastly, we might have a packed pixel, all right? So in this case, 2 bytes, if we're using an unsigned short, maybe we're using 5 bits for red, 5 bits for green, 5 bits for blue, and an alpha channel of 1 bit. So this would allow you to have a very simple image with 32,000 colors, and the ability to say this pixel is basically on or off, so when we draw it, we can skip it or not. Okay, so there's a variety of things you might need to consider for image data. And we haven't yet talked about stencil buffers or depth buffers, but those, of course, go in there. So a very common format for depth buffers is 16 bits or 24 bits, all right? And that's typically what's used. So 16 bits on, well, 32-bit floats are also popular as well, but depends on the hardware capabilities. Okay, so let's look at the different kinds of texture maps, because it's easy to think of a texture map as being 2-dimensional, but there are really several different kinds you should know how to use or be aware of how to use. The first is a 1-dimensional texture map. These are typically used for like lookups. So for instance, you might have a texture that represents black body radiation going from like black to white, right? And maybe you're just skipping the blue part, but you calculated some mathematical function, you'd like to be able to look it up. Another kind is a 2-dimensional texture. So maybe you wanted to apply some like noise detail or something, but maybe, or you have like the image of the armor that goes on the breastplate or something. You might have some 2-dimensional image data. This is probably the most common when people think of it. You could have 3D texture. For instance, if you're working with medical visualization, if you've ever had a MRI or a scan, they basically, take images at different slices, and you might want to look at or reconstruct a 3D model of this data. Okay, so 3D texture basically is a bunch of 2-dimensional images right next to each other. A cube map is useful for calculating reflections, and this is consists of 6 different images. You basically have an image for the negative and positive x-axis, an image for the negative and positive y-axis, and an image for the negative and positive z-axis, and you would use a vector, a 3D vector, that says, give me the texel for the vector pointing in such and such direction, okay? So this is very convenient for doing reflections, but these are just some representations of texture maps, probably used in the most, I guess, common scenario. Okay. So let's look about at how to address in a texture map. How do you create addresses in a texture map? So if you're talking an image, we typically use pixel coordinates. In other words, integers going from 0 to width -1. So if you're going to write to a 256 by 256 image, the leftmost pixel is at x equals 0, and the rightmost pixel is at 255, because that's the 256th element on as far as width goes. Okay, so just like a regular array in C++. Same thing for y. We'd go 0 is less than or equal to y, less than or equal to h minus 1. So whatever the height is, you subtract 1, and that's the integers that you use to address into there. And I think that it's common to use ij or xy as coordinates into this kind of a buffer. All right. Now, it's important to know that the origin is at the upper left. And that's because when you store an image inside of a file, we're used to printing things from the top of the screen down to the bottom of the screen. So we typically say that 0 is at the top of the screen for Y, and whatever our height value is actually at the bottom of the screen. Now, if you think about you're graphing, you're in calculus, you're graphing functions, you typically are more interested in the quadrant orientation, where you have the y-axis is going positive and the x-axis is, in other words, going up. Okay, and so a texture map we use what's called normalized device coordinates. Normalized device coordinates. In other words, we have values going from 0 to 1, and so we'll use typically U and V, or S and T are the typical variables we like to use, rather than like I, J, or X and Y. and we just get immediately used to saying, oh yeah, UV coordinates or ST coordinates, that's a texture map. All right, so we have some helpful ways of just reminding us what we're trying to do. And the origin is at the lower left, okay? So this is extremely important because if you're making a texture map and you're going to import it into your 3D program and then upload it, it's going to upload upside down. Because when you say row 0, it thinks that's the bottom left, okay? So there is a way, without having to go crazy, you can either go into your image editor and flip the image upside down, or when you're loading the image, you could manually just make sure that you're filling in the image array as you're loading it so that it's loading it in the proper direction. I think it's probably a little bit faster just to ignore all that and do it in the vertex shader. So as an example, if you're in your vertex shader and you have your input texture coordinate coming in, one thing you could do is you could just say, all right, let's go ahead and just create a new texture coordinate, but with the coordinates flipped backwards on the Y direction. Okay, so we keep X the same way and we do 1 minus Y. All right. So and this works too. Let's just say that you're trying to get your Y coordinate is -4 on the Y direction. Well, 1 minus -4 is 5. Okay. And well, let me think here. Let me make sure that's what we're going for. Yeah, I think that's correct. So if you're passing in 0, 1 minus 0 is 1. If you're passing in 1, 1 minus 1 is 0. And so you've flipped that around. You could also address this in the fragment shader as well by changing the coordinate you're looking up and just subtracting 1 minus the texture coordinate. The advantage to do it in the vertex shader is you do it once per vertex and not once per pixel. Okay, so some of these calculations make more sense to do it inside the vertex shader, and in other cases it makes more sense to do in the fragment shader. But in this case, I think it's a good vertex shader technique. So let's talk about what do we do when we go outside this 0 to 1 range. All right, this is an important thing. So the use case is we want to access pixels outside this range, and how are we going to handle this problem? Okay, what do you think? What should we do? I mean, if this was like any other array or any other vector or buffer, and the user wanted to get something outside the range, what would you say? What's that? Yeah. Wraparound. So wraparound is a good thing. What's also a number? I guess a typical response to somebody asking for data outside of a range. No, right? We could throw an exception. We could say there aren't pixels there. We're not going to go there, right? So wrapping around is a common way. You could just say, it's luck of the draw. You get whatever pixel just happens to be in the buffer at the time, right? This could be a real problem if you're just using the very simple y times width plus x approach, because then if you had like 0 to 255, right, the width is 256. Well, if suddenly you ask for X coordinate 256, it's not going to get the pixel after that. It's going to go all the way to the next row and grab the first pixel. So this is a real problem even in images, is you have to make sure that what do you do with numbers that are outside the range, okay? So wrapping around is common. One is to say no, which is probably impractical for 3D graphics because you typically don't want your program throwing an error. It's probably not what you mean. Okay, so there are a couple of approaches. We could do tiling or repetition. So that's the wraparound approach. All right. So if you give us a 2, right, in the 0 to 1 range, so we could say, well, you probably want the very end of 1. You want 1 instead. If you give 2.5, you probably want to get 0.5 out of the texture. So you basically can just truncate the integer that you get, or I guess the float. So if you have 2.5, you just return 0.5. If you have 4.67, you return 0.67. So you could just truncate the integer, I guess, on the left. So remove the integer portion. All right, so you could do that. Another thing you could do, and this is good, right? Because like take the wall for instance, we have this repeating pattern, or the carpet, we have this repeating pattern. So a lot of times we just want to do tiling or repetition because that allows us to use like the same data over and over again, and that's the whole idea of using texture maps. Okay, another approach is to mirror it. So as soon as you get to one side, then you say, well, let's start going back together. All right, this is called a mirrored repeat. This is useful if your texture map isn't actually repeatable. Okay, so this one allows you to make a tiling texture out of a texture that isn't tiled to begin with. All right, by just kind of going back and forth on it. And because you're bouncing between the two values, it does repeat. Okay, so this is good for some kinds of texture maps. So mirroring is one approach. Another one is clamping. In other words, you say, okay, we're going to make sure that if you go outside the range, either we return you a pixel that represents an out of range pixel, or there's another one called clamping to the edge, where we just return the pixel that's at the very edge that's closest to the one you're looking for, but on the edge of the texture map. Okay. And it sounds kind of weird to say, well, why doesn't clamping just do that behavior? And that has to do a little bit with the idea of a border color. So in earlier OpenGL, you had this border color that you could configure. So if you were to go outside the range, then you could just return the color of the border instead. So I guess that's useful if you just want to say, if they don't ask for data inside the range, then return some default answer like black or something, okay? So that could be useful. And then you have clamping to the edge, which will just return the value that's all the way at the end. Okay, so I wanted to take a moment and talk about one-dimensional textures, okay? So we introduced this concept. And so this is a case where we'd like to use 0 to 1 to look up some advanced function. We can pre-calculate the function and put it in a single array. And so, maybe we're doing a function like black body radiation, okay? Which, there's an example of black body radiation, This is not an easy calculation, or not the kind of calculation you want to do per pixel, okay? So you could use this to create a texture map. The problem with one-dimensional textures, though, is that they're mostly non-supported unless you're using a desktop graphics card. Okay, so if you want to target your phone or the web, the solution for this is to use a two-dimensional texture and just make the height 1 pixel. Okay. Now it should be, obvious, I guess, at this point, that you could use a two-dimensional texture in the same way and just use the y to represent a two-dimensional function, right? So x 0 to 1 would represent the range for the x variable, and then your vertical component would represent what happens in the y. This is useful if you're doing something like a reflectance function, where you might need to look up the incident angle and also the the direction from the light source or something. You might have two-dimensional texture for representing that. So this is one way of using those kinds of textures. Okay, and the texture arrays are another another thing that's more common than 1D textures, and this is useful for instancing. So if you're going to draw like 10 different models using the same instance or using instancing, then you could use that primitive ID to represent, okay, maybe which texture should I be using for this model. And so when you're doing a lookup in GLSL, you'll use the last coordinate as the array index. And the data is going to be laid out basically image by image. So you'll basically, so if you're talking a 64 by 64 texture, that's 4,096 pixels. So if you're doing an array of two-dimensional textures, you basically say, okay, the first 4,096 bytes is the first image, the second 4,096 bytes is the second image, and so on. And if you're going to access this, if your variable name is, say, called layer, then the actual layer that will be used is a clamp, okay, where D represents the maximum layer. So if you have like 3 layers, it's going to clamp basically between 0 and 2, because if you have 3 layers, you want to image 0, image 1, image 2, okay? So we basically take the layer, we add 0.5, and we floor it. That's our way of rounding. Okay, so we round and then we clamp. So if you're going to use this texture array capability, then just be aware that the last variable will say, okay, I want layer 1 or layer 2 or layer 5. You can actually just use the numerical index for that, and you will get the one you're looking for. Okay, so you're not mapping the last array element to like 0 to 1, which you would if it was a 3D texture, for instance. Okay. So common types of texture maps. So if you're targeting OpenGL ES 2.0 devices, then you typically can use Texture 2D and Texture Cube Map. That's what's on the table. If you're using OpenGL ES 3.0, then you can add the Texture 3D and the Texture 2D array to that. What makes that useful is that if you have some like volumetric data, then you can actually visualize it on the graphics card, in your web browser. That's kind of nice. But if you're targeting older hardware, then you're basically just limited to some, what I call just basic drawing and rendering. Now, if you're using a different version of OpenGL, like desktop OpenGL, then that opens you up to being able to use like Texture 1D array. And there could be many possible vendor formats as well. OpenGL is kind of made to be extensible. So although I think, I mentioned this in the class before, it's better to target like the lowest common denominator for graphics and work around that than it is to just try everything brand new under the sun. Because as soon as you try to run it on a different computer, you're going to find out that this is an older graphics card, doesn't support it. So it's better if you're building an engine, unless you have a specific need to use a more, I guess, I don't know the right word, but at the second. But if you're trying to use something that's more obscure, then you're less likely to have an audience for your product, okay? So I think lowest common denominator is a better way to communicate your 3D ideas to other people. So keep that in mind. Okay, so powers of 2. All right, so we're talking about textures. We need to just be aware of 1, 2, 4, 8, 16, so on, because texture maps need to be a power of 2. So it doesn't have to be like the width and height has to be both the same, but you might have 1024 by 512, 2048 by 2048, 64 by 256. And there is an important reason for doing powers of 2, and that has to do with the easier to address, right? So we can use very simple shifting. If we want to do multiplication, right? Like lookups, like y times width can just be y shift lefted and this power of 2 that we're using. So it's very quick for hardware to address into these texture maps with a power of 2, and it's also easier to do what I call, what's called MIPMAPPIng, which is where you create approximations of this image so you can handle the problem of when the image gets smaller when you're trying to read from the texture map. We'll take a look at mapping in a second. Okay, sometimes we can use a texture rectangle, and the difference between this and a regular texture is that we can use pixel coordinates. So we can say 0 to 123, and that represents pixels 0 through 123, x equal 123. However, this does not support MIPMAPPing, which means that this is good if you just want to copy image data to the screen and you don't want to do texture mapping. Okay, so let's take a look at MIPMAPPing. MIPMAPPing handles the problem of magnification and minification. Well, not necessarily magnification, but more minification. So what happens if you're trying to sample a texture map? You'd like to be able to, you know, as the image gets smaller, you're at a choice like, okay, I have 4 pixels that could all be completely different colors, but which one do you pick? Okay, so in order to do this, we can create levels of decreasing resolution. And if you reduce by a half, then you take the limit of that geometric series and you basically only add 33% more data. So if somebody said you could have substantially increased image quality just by adding a third extra data, that's like a yeah, sign me up for that. That's something you can handle, right? So if we have a texture map, we might create some smaller and smaller versions of that texture map. And this is how MIPMAPPing works. So then if we're drawing, we can use the MIPMAP levels to decide which one has the appropriate amount of detail for what we're trying to draw. So we would like to not pick a texture map that's too detailed in an area where we need less detail, okay? So in order to solve this problem, we use sampling, okay? So this is some terminology you should be aware of. Sampling is like, where do we look for our data? So I grabbed this image from Tom's Hardware, and they're comparing, let me turn this down so we can see it. They're comparing different kinds of MIPMAPPing sampling, okay? The first one is called point sampling, and that's where we just say, we're just gonna use the main texture, and we're just gonna pick the closest pixel, all right? This is, you know, over here it looks rough, although it's hard to tell perhaps if this is just too much detail or if this is too much detail, or on the other hand, just turns into a giant sparkly mess, okay? So we'll take a look at an example in just a moment. Okay, the second one is we're not going to use MIPMAPPing, but we're going to use linear sampling. So this has to do with magnification. This is what happens when I'm blowing an image up, right? Do I just pick the closest one, or do I blend between the pixels that I'm in between? All right, so linear sampling is blending neighboring pixels to get, and this is what that blurred look kind of looks like, okay? So we would say it's pixelated if we are using point sampling, and it looks blurry if we're using a linear sampling. And that's just how that territory goes. You can't really make more data when you don't have any. The second approach is called bilinear sampling. And what that does is we're going to, if you look very closely, you'll notice that over here it almost looks like a line, and it goes to about over here. And you can tell that we basically, this bottom layer, we're at level 0. And then over here we decide, okay, that's getting too small, so we need to switch to the next MIP level. So we'll start using this image. So obviously this will look blurry because we have to blow it up. Then as we get to over here, then we need to grab the next sample, which is down over here. So you'll see a line over here, and this will go up, and this looks like the last line. And you'll see that this gets really blurry, and that's because we're using a small texture map over here. And it makes sense that it would be blurry because if you had a 64 by 64 texture map here, then this is 32 by 32 pixels, and this is 16 by 16 pixels, and this is 8 by 8 pixels. So as you're getting down there, you're using very little image data to reconstruct it, okay? Now, in motion, you can tell these, you can tell on a regular image that this is better than this result, because you can still get the sparkly effects over here. But the problem here is that you notice these lines, it causes a decrease in quality, okay? So the next version of filtering we can do is called trilinear filtering. And instead of just picking the one MIP level, we actually take the two neighboring levels, this level and this level, and we calculate an in-between value of what would it be if I had sampled this MIP level and this MIP level. And so as I'm going from level 0 to level 1, I'm blending those two results together. And so as a result, when you have trilinear MIP mapping, it goes smoothly from the first level to the last level. But you don't notice this line anymore, but it does get blurry pretty quickly. Okay, so it doesn't take care of the problem of blur, like, so this is something, we have two ends of the spectrum. On this one, we have point sampling, and this just means we have too much data. Over here, we're trilinear mapping. It looks better, but now we don't have as much data. But we do have the data. Okay, so what we can do is a technique called anisotropic filtering. And so what we'll do is we'll take a few samples from the original texture map and figure out, well, what should the value be for that texture? And so when you use anisotropic filtering, we're typically still blending back to front, but we're also not losing the detail we have in the higher level of MIP level, okay? So as a result, this one looks nearly as good as trilinear filtering with very little sparkling effects. So it looks particularly good. Typically when I play games, if I was given a choice between anti-aliasing and anisotropic filtering, I always go for anisotropic filtering because it makes the image more clear, and it's a lot less expensive too than anti-aliasing. Okay, so those are the different kinds of sampling. I thought we could take a look at texture mapping and see what's going on. So I'm going to go over here to my texture demo, and I can basically change the filter. The easiest one to see is the magnification filter. So if I turn on the magnification filter, I can immediately see that we're just blending pixel to pixel. All right, and so depending on what you're trying to do, I might think that's better or I might think that's better. It depends on what it is. Okay, so if I change the texture map, let's go. This is still pretty high resolution, but I think this is the best one because this is deliberately low resolution, right? So I'm going to change the orbit speed on this, so we get the texture map kind of rotating, and you will notice as we get to these off angles that in this case we're the MIP level. I think we have MIP mapping enabled, but it's picking a lower, I guess a lower resolution for those. All right. So we get some issues there. If I were to turn off the magnification filter, you'll notice that we get a little bit of some sparkly artifacts. This isn't the best way to show that though. So I'm actually going to minimize everything. Pull up. Sure, pull up Descent 3. So sometimes it's easy to see it in a game context. So I'll load up a game. And hopefully this doesn't take too long to get going. Oh, actually, it did start over here. Set up DirectX video, OpenGL. That's fine. Okay. Let me see if I can put this in a window. Okay, so we're going to, I'll just pick that. I just make a new game and we'll just pick the original. Skip the videos. Is this showing up on your, okay, it is. I would see it in there. Oh, gotcha. Because it's changing the resolution. There we go. Okay. So over here, we have, I can basically, we can change some of the settings on here, but you can see right now that the default is using bilinear filtering. And you can tell that with the texture maps on the ceiling. You notice how it goes from like high detail to low detail, and it's fixed, okay? So it looks better than if I turned it off. So if I go here and I turn off, say, MIPMAPPING and bilinear filtering, for some reason it thinks it needs to reset the entire video display. It's an older game, so I guess that's normal. Restart the engine. That's the kind of the mindset there. Maybe I should have picked something else. I'm going to do that. Okay, new game, rookie. Okay, this is a lot faster. Okay, so over here, I think we just have the default, you know, no texture filtering at all. The problem is that if you look at the, you know, if we look at the distance, then we get this flickering occur with the lights at the end of the, you know, sometimes that's just a pixel by pixel thing, but essentially it's caused by just not enough resolution. All right, so we have to like pick. Is it going to be white? Is it going to be red? What's going on here? Okay, so if let me hit detail levels, custom. Oh, this almost feels like an example of like single buffering. If I rotate, sometimes you see the image tearing. I don't know if you can tell that. Okay, so there's a good reason why you do double buffering if you can. Okay. All right, let's see here. Okay, so I'm going to close that. I guess that illustrates what I'm trying to get across. And we'll turn that off. Okay, so if I go back here, so what we were trying to get is just see the problem as when you're far away, you know, what ends up happening. Okay, oops. I meant to go over here. Okay, so we have this OpenGL example. So if we turn on some basic filtering, all right, then we notice that the image quality gets better. But you'll notice as it gets close to, I guess, adjacent, when it starts to pick up on the low resolution, it looks like it's really blocky towards that edge, okay? So maybe I can time it as we get closer there. Okay, so this is a good example. We have lost a lot of the detail, and you can see how pixelated it is. That means that we picked the wrong level. So if I go with no MIPMAPPing, this is what it would look like. If I pick MIPMAPPing, then we can see how it's choosing a smaller level of detail. If I go with these other, they basically add filtering to the MIPMAPPing. So this one is filtering it, applying linear filtering to the smaller MIP level. And then this last one is doing trilinear filtering, which you can tell it looks blurry. Okay, so it looks blurry. We can also add the magnification filter in there. Now, when we do anisotropic filtering, we can basically choose how many samples we would like. So if I just do one sample, it's not very, I guess, not very high resolution, I guess. If I go 4, it's still kind of subtle. Let's see over here. I guess it's all subtle. I don't know if it's I don't know if it's doing anything. Could be I'm not giving it enough to work with. Oh, I know why. It's a low resolution texture. So let me turn on high resolution texture. Okay, so see if that makes a difference. Able to see the difference as the speed changes. Unless anisotropic filtering is not supported. Yeah, it's on there. Okay, so all right. So as we basically get to the edges, it should be, I guess, doing. That's not anisotropic. I can tell. The filters being interfering with your. I don't think so, because on this one, and this is a good example of that. If you just do point sampling, it can look really bad. Okay, so the texture is obviously too high resolution, so it would help to turn on, I guess, MIPMAPPing. So you can tell immediately it makes a huge difference. Okay, just using smaller images, but it doesn't solve the problem of the filtering. So we can turn on, I guess, bilinear, and so we're getting the blending there, and then trilinear is making sure that it's smoothly going from level to level. Okay. Okay, so these make a big difference in quality in terms of using the right filters. But you know, I could see if you're doing a pixel art game how that would just kind of ruin your day to have it blurred out, right? But you can definitely use these to, depending on what you're doing, to help increase the quality. Okay. All right. So I'll minimize that. Okay. So that's the texture mapping example. I did want to look at an example of using fonts. All right. So if you're doing OpenGL or any kind of graphics thing, and you want to put text on the screen, it's not as simple as you might think, because the tools that are available, we have a vertex shader, we have a fragment shader, we have texture maps now, and but we have no way of basically, or we could draw the geometry on the screen if we had shape information for each letter, but that can be a little bit more involved, because then you have to come up with the shapes outlines for the fonts. So one way to do it is to use bitmap fonts, and bitmap fonts, we're basically going to store all the glyphs in a texture map. Okay, so if you're looking at types, a glyph is basically one character. Okay, and we can store all those in a texture map, and then we can render a quad. So typically using 2 triangles, and we might have the our source image here. So let me move this out of the way. So we have a texture map, and maybe we've packed in a font into this bitmap. And so we can say, where does that image start? So like W might start at 0, 0 and go for however wide W is and however high W is. And then we can use the X offset and Y offset to figure out where should we put it? All right, so for example, a period, obviously we need to have a big Y offset to put it down where it's supposed to be. But this is a convenient way for us to be able to support, packing a huge power of 2 texture with fonts. I'll show you this program in action, and it's pretty cool. Okay, and then our X offset and Y offset. So we talked about X offset and Y offset. So that's where we should draw the glyph in respect to where we currently are drawing the next character. And then X advance is basically how many pixels should we go from. So if we're drawing letter I, obviously we don't need as many pixels to go forward as we do with W. Okay, unless you're talking about a fixed format or a fixed width font, where you have like 8x8 or 9x15 or whatever the bitmap size is, and then you can just advance a fixed space every time. Okay, but typically for reading, unless you're going for that classic vibe, it does make sense to be able to have a font that is variable or proportionally spaced. Okay, so the font data for this particular program kind of outputs some convenient information. So we can get the size of the texture map, the image that the texture is located in, all the, each character. So 32 is the number 1, 33 is the number 2, 34 is the number, and so on. And so we can basically figure out where do we need to grab this sub image from the texture, from the from our font bitmap, so we can go ahead and draw the next character. Okay, so I've been playing around with Allegro 5 this week, which is another kind of graphics library. And so I was writing basically, I don't know, yesterday I was like, let's do fonts. So I was sitting down after dinner and doing fonts. But the idea here is that I can basically load up a bitmapped file, and then I can draw whatever I want. And then I did it so that I could basically specify the size of the box I want to draw. And as soon as it would get to the end, it would wrap around and continue drawing to the next line and so on. Okay, so if I was doing this, I could make my own little message box if I wanted to. So I figured we could take a look at that and look at an implementation detail. So I'm going to go over to Allegro example. And whoops, zoom out a little bit. Okay. All right, so if you've never used Allegro, I figure we could use this as a quick how-to. Allegro is a game library that's been around for a long time written by a guy, Sean Hargreaves, I believe. So it's over at libaleg.org. And this is a cross-platform library. It works on Windows, Linux, Mac OS X, iPhone, Android. It uses C, so you can use it in C++. It makes it pretty convenient. You get hardware-accelerated bitmap and graphical primitive drawing support, audio, font loading, video playback, a few other things. So if you're looking for an all-in-one, you'd like to be able to write software from scratch, then this is a pretty good way to do it. And there's 2 versions. One's Allegro 4 and the other one's Allegro 5. And they have a lot of useful documentation on the library. So if you're trying to figure out how to set the display mode or whatever the case, you can go ahead and do that. If you need to load images, it has support for doing that. All right, and I'll show you how you do it with the SDL2 library as well. They have an image library. Because getting images into your program is not as easy as it sounds. You do need some kind of external way of doing that. Okay, so just to kind of take a look at this, let's see here. This is, I need to go. I'll show you some of the images here. So let me just open this up in View. Okay, so these are some different fonts. So this is like a Commodore 64 font, and this is a Gothic font. In other words, it's It's not got serifs on it. So this one I have a bold and italic, regular italics instead of bold italics. This is and then the regular one, and this one is a sans serif. This is a serif font. In other words, it's got the little marks on the characters. So if you're looking for, you know, a lot of times you're interested in just making a font. So in the United States, bitmap fonts are not copyrighted because you're not storing information. It's just like it's like an image. But normally the true top, the font outlines are copyrighted because they're really represent a computer program for how to draw those characters, and they're not the characters themselves. Okay, so that's just something to keep in mind. Although I would choose a font with an open source license if you're planning on doing that. This particular font, BM font, allows you to basically load up whatever font you're interested in. So maybe I'm interested in URW geometric or something. And I can set the size. So maybe I'm interested in like a large, and this is where you basically, you know, make a choice on how you should do it. So I'm going to pick that size. And if oh, maybe that was too big, font settings. Let's just go with 32. Okay, I'll go with something smaller. I'll just do 16. Oh, no. I have to select the characters. Okay, that's too small. Let's go here, and let's just say I want some really big characters. So this is an example of the texture map it would create. It would actually pack as many symbols as it can on a single texture. So if I was maybe doing this with one single texture, I might say, let's use a 1024 by 1024 texture map. There we go. And then if I wanted to, now I can actually use a, you know, something really big, 128. Okay. So if you're looking for something that will generate like a high quality outline for you, then what you can do is take this this image with the metadata, and then we can copy these out of this texture map and draw them. Okay. So with Allegro, I just wanted to copy the sub images out and then just draw those images like they were, as if they were sprites on the screen. Okay, so that's kind of the premise there. And then if you wanted to pick something, you know, that was maybe you're looking for an open source font, like maybe you like Helvetica, and Helvetica is not free, so use this Heroes font, Texture Heroes. And so now you got some Helvetica that you can use inside your program for free. And then it's because it's bitmapped, you don't have to worry about how this is exactly what's going to be drawn on the screen. So this is useful. Okay. So BM font, pretty cool tool. And so then what I need to do is, let's go Visual Studio, is I need to be able to extract this information. So I have a pointer here to the bitmap, and over here, here's my font class. So I'm going to load up a font, and I have a few things that allow me to set the box that I'm writing inside of, a way to move my current position inside that box to wherever I want. And then I can put a single character, or I can write a sequence of characters out to the screen. And advance will just move me to the next line. Wherever I'm at right now, it'll just move me down one. Okay. So line height, this is basically represents, you know, how tall are my characters. And over here, I have a map. I'm just using a map so I can get that. It's easier to do it this way if you don't, because your characters are coming in like character number 32, character number 48, that kind of thing. Okay, so let me skip down here to the drawing part. Okay, so load font. I go ahead and I have a PNG I'm going to load and a font I'm going to load, which is the metadata for the font. And so I'm going to go line by line and tokenize the string. So if it starts with char, then I know that I'm going to get the sequence of data. So the source, the X, Y position, the width and height, X offset, and all that. And then if I've loaded up my bitmap, then I can go ahead and copy out. This is using basically, this is like bitblit that we talked about. I can basically say, where's the XY position and width and height, and then I'm going to draw it to a new bitmap in the top right corner. Okay, so then when I want to put a character, then I can just, if I'm getting a carriage return or a new line, then I can advance it to the next line. And then I can look for my glyph. So if character C is, 48, for instance, then I can look for my glyphs inside my map. And then I'm going to make sure that that it's not going to go past the end of the box, right? So I take my current X position and I add the advance to it. And if it's greater than the box width, then I say, just go to the next line. And then we can go ahead and draw the bitmap using the X offset and the Y offset. And that's important because some of these characters, like, like a period or something, it's going to end up going down. We have to offset that so that it is drawn on the appropriate element of the line, okay? Okay, so that's how we would draw a character. Otherwise, I had a case where I was debugging. I would just draw the rectangle that it would be fit in. And then I advance the X position by the advance, all right? So the X advance is, like I said, how many pixels do you have to go? All right, put string is just we'll take every character and then call put. And advance just moves our X position back to 0 and adds our line height to our Y. Okay, so let's take a... So if you've never used Allegro before, you generally have to initialize it. So you call the initialization library. We have to initialize the add-ons, like the image add-on, primitives. I'm not using the font one. I might use the audio one. And so we will install some threads basically to handle the mouse, keyboard, joystick, and the audio. And then we set our example, our title for our title bar is Allegro example, and I create the display using the width and height I've determined I'm going to use, okay? And then like most graphical user interfaces, you typically use an event queue. So I create an event queue and I'm going to process events as they come in. The one I'm interested in is basically, did I press the escape key? And if I press the escape key, then we'll just exit the main loop. All right. Then what I do is I need to clear the back buffer. So over here, I'm drawing a border and like a center screen. And then I'm just cycling the color on the border. And then down over here, I'm actually using blending, which is something we'll talk about next week. But the idea here is I'd like to use the alpha channel of the font to go ahead and blend in with the destination, okay? So in other words, if you don't do that, then you don't get font anti-aliasing, all right? So you either can use font anti-aliasing or you don't have to, okay? So I think in this one, I have to fix one of these. So I'm just gonna pick one that's not a fixed width font, and I'm gonna go ahead and just draw onto this one. Okay, and so we can see here what happens when you accidentally mess it up, all right? So in this case, I'll just put the magnifier on real quick so we can see what's going on. Okay, so over here you can see that we're drawing each character, and even the space characters are pretty small. Okay, but then when I get to the end of a line, then it'll just go back to the beginning. All right. So in order to correct this this issue, I need to put the basically I want to have colored text. So that means that my characters need to be white on my image, and the alpha channel needs to correspond to whether it's visible or not. And if it's white, then basically I can multiply it with any color I want and turn it into the particular color. So let me fix the. Let's go ahead and fix this font issue. So I was using the IPA. Where is it? Oh, I was using this on a different computer. That's okay. We'll pick a fun one. I'll do IMThal English Pro, and I think I'll just go with 16 characters. And do super sampling. All right, that's too small, so I need to adjust this. So I'll just say 256 by 256. And we want white text on black with alpha. I'm going to save that as a PNG. Okay, that's still too small. Options. Oh, I need 20. I want 24 pixels. That's looking okay. Let's just use this a little bit smaller texture map though. And we want to include all the bottom characters. Options, I guess I need to unselect them all. Oh, that's what it was. Okay. Yeah, if you know you're just going to use ASCII, then you just select the ones you want. So that looks good. So we're going to go ahead and print this, save bitmap font as. Go to I'm going to call this English Pro. Okay. Just to show you how easy it is to load this stuff up. There's my fonts.